Assalamualaikum, Mr. Jamal.
Waalaikumsalam warahmatullah.
Thank you very much.
I'm sorry.
For coming. So we appreciate you joining us this morning.
Thank you.
So, okay, Wenzi and Chapa, so I think we can start now.
Yeah.
Is it okay?
Yeah, sure.
Okay, thank you very much.
So, good morning, everyone. So, thank you for your participation. So, we are here today for the second WESTPAC workshop on upwelling and its dynamic in the South China Sea and its adjacent areas. So, for your information, the first workshop was held in May 2018 in Putrajaya, where almost 30 scientists from more than 7 countries was there to provide the foundation for the group. And today we are proud that many of us are basically coming from different parts of the region, and hopefully we can have a fruitful discussions for the next 2 days. So I believe that many of you are already familiar with the online webinar station, but we hope in the future we can still organize a physical face-to-face session. And we also hope that all of you are healthy and staying safe no matter where you are. So we pray that the situation will be better soon. And I'm Zuraini Zainal, the MC for today. And with me is the principal investigator for this Upwell group, Associate Professor Dr. Fazil Muhammad Ahir, who will also act as a chairperson for this event. And our IOC-WESTPAC Secretariat led by Mr. Zhu Wengzi and Ms. Nachapa are also here from Bangkok. And thank you for all for your efforts in making this program possible. And with us is also Dr. Ernest Koch and all INO Secretariat who has helped in organizing this session. So we would like to express deepest thank you. And I would like to thank all the invited speakers for your willingness to share your knowledge on this subject. So before I pass this session to Dr. Fazil, let me provide you with a little information that you need to take note during the session. The first one is you have to remain on mute when you are not speaking and unmute yourself only when you want to speak. And the second one is to use the chat as the back channel for questions and comments. So now, please allow me to pass the session to the chairperson, Associate Professor Dr. Fazil Muhammad Ahir.
Thank you very much, Dr. Zuraini, for the kind introduction. So I would like to say welcome to all of our participants today for joining us this morning. So this is a very interesting, I think, way of having our workshop, because our first workshop was in 2018. It was held in Putrajaya almost 3 years ago. We always planned that. Actually, we planned to have a proper meeting last year, but somehow, we can't organize it. I think our partner, Prof. Ishaq, was already agreed that Indonesia will be our host for this event, but unfortunately, we couldn't manage to organize it, physically. So we have it today in an online form. So, but I really appreciate that all of us can really join this program today. So for your information, I just give you some brief introduction. So this group was set up in 2015, I think during the WESTPAC Intergovernmental Session it was in Phuket at that time. And it was started with 9 supporting countries that involved with the programs. The mission is very simple. So our region are blessed with lots of small scale upwelling, but most of this area is not well documented and explored. So we plan to provide the knowledge for this area, trainings to the young scientists, and also explore those beautiful ocean dynamic system in this region. So all of our speakers today will tell you more about that later on today. So I would like, but first of all, I would like to invite our representative from the Ministry of Environment and Water, Malaysia, Mr. Jamalulail Abu Bakar. Thank you very much for coming and joining us today. And I hope you can, you can give us, short remarks on this program for this morning. So over to you, Mr. Jamalulail.
Thank you, Dr. Fadil. Dear colleagues, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and a very good morning to everyone. I would like to convey sincere regard from Dr. Nagu for not being able to be with us today due to some urgent matters that he needs to attend with the minister. So it is my great pleasure and honor to welcome you to the second WESTPAC workshop on upwelling and its dynamics in South China Sea. And I would like to take this opportunity to thank the Intergovernmental Oceanographic and University Malaysia Terengganu for co-hosting the workshop. And I thank everybody who was involved in its preparation. A special word of gratitude to the principal investigator, IOC-WESTPAC Upwelling Group, Associate Professor Dr. Muhammad Fadil Akhir, Secretariat of IOC Subcommission on the West Pacific WESTPAC, Mr. Zhu Wenzi. Our keynote speaker, Associate Professor Dr. Joshan Kampf, and dedicated panelists from Japan, China, Vietnam, Philippines, Thailand, Russia, and Malaysia in steering our regional efforts to achieve our sustainable development goals according to the UN Decade of Ocean Science. It is indeed our great pleasure that UMT is hosting this workshop for the second time after we had the first one physically in Putrajaya in 2018. And once again, this year we look forward to receiving full support from the Intergovernmental Oceanographic Commission, IOC. Colleagues, ladies and gentlemen, this year will mark the beginning of a very challenging and yet interesting journey for us in empowering the UN Decades of Ocean Science. And I believe all member countries are very excited to take this journey, thus really change and provide a better future for our ocean. So we are here today to look into our common concern of upwelling systems in the region. As we are all aware, oceans and seas cover 2/3 of our home, and maybe we could change its name from planet Earth to planet water. Oceans provide food, energy, water, jobs, and economic benefits for people in every country, even those that are landlocked. They are a crucial buffer against climate change and a massive resource for sustainable development. The health of our oceans and seas is inextricably linked with the health of our planet and all life on Earth. Many nationalities, including mine, have a special relationship with the sea. And the truth is, the sea has a special relationship with all of us, and it keeps us alive. Dear colleagues, ladies and gentlemen, I once again would like to applaud the dedication of Associate Professor Dr. Fadil and his team from UMT in exploring the dynamics of South China Sea, which acknowledge an area that was almost neglected due to its shallow shelf. However, based on the scientific research, the perspective changed and put significant effort which led to insightful knowledge about this region. Upwelling is one of those dynamics that have been discovered by their team in this region. As you can see, our agenda of the 2 days workshop is impressively rich with discussion of the overview of the oceanic processes that enhancing nutrient fluxes at continental margins, upwelling data analysis, future plan for upwelling studies, and knowledge sharing on the regional data analysis from the speakers. Together, we hope that such collaborative effort like this provide the best possible outcome that will make the ocean a better place for us. Ocean is a God gift for us, as we also live by consume what are being adopted by ocean for us as a mankind. So on that remarks, I would wish once again to encourage all participants to actively engage in our discussions and debates of the coming days, and to share their country's experiences and not to hesitate to ask questions, not only to our expert speakers, but also to one another in order to make this a truly interactive and lively event. And with that, I would like to thank UMT and IOC and the WESTPAC for organizing this workshop. And Assalamu alaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullah. Thank you very much, Mr. Jamalullah, for your kind introduction to the program, for officiating this very meaningful workshop today and tomorrow. So, for your information, I think this year will be a special year, and not only this year. I think these decades will be a special decades for all of us, especially the one that working with ocean science. So I would like, talking about United Nations Decade of Ocean Science, there is lots of things that we plan for it, at the global or international level. So I think that's the best person that to explain about this is none other than Mr. Zhu Wengzi, our head of IOC Subcommission for the Western Pacific. So please, Wengzi, the
Thank you
floor
very
is
much.
yours.
Okay. Good morning, everyone. So thanks very much for joining this. I would like to express our sincere thanks, particular to, Dr. Faisal and your excellent team for taking a lead in organizing this team. It's also a great honor for us to have, the Professor Noor Ali and also Park Jama from the ministry, and also Dr. Vosudo and the WESTPAC chair and all, other WESTPAC colleagues to join this meeting. I think which means a lot, particularly at the beginning of the UN Decade of Ocean Science. I feel this is probably the first large-scale workshop we organized at the beginning of the UN Decade with the participation of almost 100 people from all countries in the region. So for that, I really appreciate the great efforts have been made, particularly by the Institute of Oceanography and the Environment of UMT, and also the Ministry of Environment and Water. So I think just, for some colleagues, maybe you have heard many times of their presentation about the UN Decade. But for some colleagues, maybe you're not very well of this UN Decade. So for those people who have heard many times, please bear with me, on this presentation. So I will give a very short brief about the UN Decade and what's going on and what our perspective for the future. I think most of us has been very well. Recently the ocean has been increasingly raised over the last 5 to 10 years on many international political agenda. There are a lot of number of international agreements that are related to ocean. So we have the famous SDG with their, standalone SDG 14 on ocean. We also, have the UNFCCC, focus on climate change consultation. So which also put ocean as a, key area for climate change adaptation and also mitigation. We also have other, international program, international agreement focus on the small island developed country and also the disaster risk mitigation. So I think, over the last 10 years, with so many, high recognition on the ocean and the importance of ocean science, that's formed a strong need for us to initiate, particularly for IOC, UNESCO, to initiate the UN Decade of Ocean Science. So because UNESCO and its IOC firmly believe there need to be nothing short of a revolution in the generation of use of science to share the reliable information on the ocean in order to support the formulation of sustainable policies and also to support the sustainable ocean economy. This is why 3 years ago, the IOC UNESCO initiated this very difficult international process, for the UN Decade. And finally, it was adopted by the United Nations Assembly in late 2017 with the UNESCO IOC mandated to coordinate the preparation and also preparation of the UN Decade of Ocean Science. So in one word, I think it's a key word, the UN Decade of Ocean Science for Sustainable Development aims to support, the global efforts to reverse the ocean health decline and also engage all ocean stakeholders, not only scientific communities, but all ocean stakeholders, to work behind a common framework that can ensure the ocean science can fully support a country in achieving the sustainable development of the ocean and other international ocean-related framework. That's why I think the ocean scientific community had a very key role to play in this ocean decade, particularly not only to generate the science, but also need to engage other stakeholders into the ocean science development and also application of the ocean science to sustainable development. So you can see over the last 3 years, a large number of global thematic and regional planning meetings have been convened, by IOC globally, regionally, even nationally, try to engage a wide range of ocean stakeholders, including ocean scientific community, governmental agency, UN entity, NGO, private sector, donor agency, across all ocean basins. So that process has resulted in the final version of the decade implementation plan that was officially adopted on the last day of 2020. So the implementation plan was still very fresh. It was just officially approved by United Nations General Assembly on the last day of last year. With IOC was still continued mandated to lead the implementation of the UN decade for next 10 years. So the vision of the ocean decade is quite clear, formulated as the vision or the science we need for the ocean we want. So the key role I said, ocean scientific community must play a key role, take a lead in this ocean decade by engaging all ocean stakeholders to developing the ocean science to serve the needs of ocean stakeholders. So the mission of ocean decade is to catalyze transformative ocean science solution. So here we need to pay attention to the keywords here. One is a transformative, second is a solution. So the transformative things for me is, one is to really make science more relevant to sustainable development by engaging all kinds of stakeholders into the process, and thus lead to their finally leading to their ocean science solution for sustainable development, and also putting the people in the whole process as a core position in the whole process. Next, I will see. So the ocean decade will be implemented on a voluntary basis. So this is what ocean we want for the future ocean that has been universally formulated by the whole global, communities, including clean ocean, healthy ocean, resilient ocean, productive ocean, predictive ocean, safe ocean, accessible ocean, and inspiring and engaging ocean. So totally 7 societal outcomes that formulate the vision of the ocean we want. So the 10-decade challenges, same time, was also formulated at this stage, aiming to, aiming to understand and act on providing solution to marine pollution, and also to mitigate, provide solution to mitigation of their impact, to monitor and manage and restore ocean ecosystem and their biodiversity. I think this is also very critical relevance to our region as well. And third, to also, to have ocean to be more sustainable, productive due to the large population of our, region in our people in this region. The fourth is to develop a sustainable blue economy, and also including ocean climate and lexes, and also need to develop their multi-integrated ocean observing system, multi-hazard warning system, and also, to develop a digital representation of the whole global ocean. So all the 8 challenges will be, underpinned by capacity building and also by ocean literacy in order to improve the value of ocean, improve the value of ocean science in all social communities. So this is the 10 ocean challenges has been formulated at this stage. They are very much closely related, as you can see, and also mutually support each other. So with all feedbacks, I think, IOC initiated also the implementation plan development process. So that has been adopted, I think, as I mentioned last month by the United Nations General Assembly. So this is the decade action framework will get the future design and implementation of decade actions or initiatives. So the Ocean Decade Challenge will form the highest level of this framework that probably will be represented by future UN Decade Program. So that represents the most immediate and present priority for the UN Decade. So aim to unite the all decade partners in collective actions at global, regional, national, even local scales. So the Ocean Decade objective form the second level of the framework. So including very simple 3 objectives from identification of required knowledge for sustainable development. So this is the basic starting point for ocean science. We need to identify required knowledge for sustainable development. And the second objective, to build the capacity and generate knowledge. The third objective, to increase the use of ocean knowledge to develop sustainable development solutions. So the decade actions are, currently are, represented in 2 different forms, namely decade program, decade project, decade activities, and the decade contributions. So the all 4 category of decade actions actually, represent the, activity, in different level in terms of the geographic coverage, in terms of duration, in terms of contribution, in terms of multinational or national, nature. So from this slide, you can see the difference. And also our IOC and it's established EPG, Executive Planning Group, also are devised or formulated the endorsement process for all proposed decade actions. So for UN, 9 UN entities will just seek endorsement of their UN decade actions. I think for 9 UN entities will seek endorsement. For UN entities, including IOC, will just simply register your actions rather than seeking endorsement, given the different UN governing structures, for their financial and program issues. So this is something to ensure success. The decade, I think, as I emphasized many times, must engage diverse stakeholders, including all different kind of communities, particular national and subnational governments, UN agencies, business sectors, NGOs, even local communities, particularly our early career ocean professionals, because the decade will last for 10 years. Our young early career scientists will play a key role in the next 10 years. So in that sense, I really wish to encourage our young scientists to display your leadership, to start to develop your network to further advance the international marine science cooperation developed in the region. So as you remember, the first call for the UN decade had been launched in mid-October last year, with a deadline for submission set up as mid of January this year. And certainly for the future, there will be regular calls for decade actions through the whole 10 years. So taking this opportunity, I would also update you with the latest submission that IOC had been received in response to the first call. So a total of 213 program proposals have been received, and also 27 large contribution submission also received from national governmental agency, donor agency, private sectors at this moment. So the whole IOC, together with their EPG member, in the process of reviewing all the proposals have been received so far. So meanwhile, IOC is in the process of setting up a UN Decade Advisory Body, who is mandated to review and endorse all the program proposals received globally. So the final result for the endorsement will be released in the mid of March based on the current schedule. So scoping down to this region, I think IOC-WESTPAC has been working very closely with other UN agencies, national agencies, institutions, and also universities. are trying to set the stage for decade action in this region. So we have organized several online or even physical workshop in late 2019, and also a lot of virtual meeting consultation last year, 2020. Yeah, more than 100 consultation has been organized virtually last year with, with a different group, different stakeholders. So I think there are a lot of those consultations reflected a very high level enthusiasm ocean stakeholder in the region for the decade, and also result in a very long, non-exhaustive list of potential proposals that we can further formulate over the next 10 years. So we're also considering, developing our decade regional conference series in conjunction with the international WESTPAC International Marine Science Conference once every 3 years in the region, hosted by country on a voluntary basis. That will include high-level statements, a plenary panel discussion, partnership and stakeholder dialogue, and also parallel science discussion structured around the decade and region priorities. We are also developing, the demand-driven, co-design and solution-oriented decade actions, including project, building on but not limited to existing regional program and national program. So there are several proposals already in pipeline. Now we are waiting for the next opportunity to submit. So in that sense, I would strongly encourage you, to start considering the possibility of developing our Ocean Decade proposal. For this group, I think tomorrow, I very, very much look forward to the discussion tomorrow. What kind of outcome we can, achieved, in order to formulate a possible proposal for the UN Decade of Ocean Science. So certainly, all those kind of activity won't be developed by the subcommission alone, but via a various partnership with the UN agency, national agency, research institution and university, and also private sector, and also donor agency as well. So last slides, I think as I emphasized many times, this is not only our decade belong to IOC, not only belonging to ocean science community, but also to all ocean stakeholders. So, so there are several engagement mechanisms. I think IOC has been, the UN Decade has been formulated, in their implementation plan. So first, I think very important, you can propose, lead, and participate in the decade actions, either program, project, or activities. You can also become member of the Ocean Decade Alliance that will be established in the mid of this year to provide your support, your idea, and also to network, your peers in a broad context of Ocean Decade that can provide it. And particularly for our young generation, I would say the early career ocean professionals, I think indeed it's a good opportunity for you to start to display, to demonstrate your leadership, to work together with other young scientists or young professional, ocean professional from other countries to develop the UN Decade regional early career professionals for this region as a part of the global early career ocean professionals to make our regional voice, heard at the global level, and also to translate the global objective into the concrete actions on the ground. So this is something, thank you very much. We look very much forward to working more closely with all of you in the UN Decade Ocean Science. We would also encourage you to disseminate this information and also to start to build your network, stakeholder group within your network with the other ocean stakeholders as well. So wish you, all the best. I think let's jointly overcome the present challenging moments. I look forward to see you all physically in a very near future. Thank you very much. Yeah,
thank you.
Thank you. Yeah.
Thank you very much, Wendy, for your introduction on United Nations Decades of Ocean Science. It's a very huge, I think, effort globally and it's we hope, all of us hope that this can change lots of things on how we interact with our oceans. But of course, I would like to capture some of your points where I think the idea of these ocean decades is not easy. I think the discussion part starts like 3 years earlier or 4 years earlier for this 10 years program, and what we want to look at is how we can transform ocean science solutions so we can have a sustainable development and connecting peoples with oceans. So I think that's the best idea. And your last point on scientists, young scientists, young researchers and young people. I think that's also very important, because we try to we want to have the ocean we want by using the science that we produce within this period of time. I think that's very critical for our future. So give me some. I will describe you what's our plan today for the whole programs. So I think this morning, so the program will be a 2-day program. What we're going to do today is basically a presentation from all of our experts on the topics of upwelling, and most of these upwelling sites come from within the South China Sea and adjacent seas. So we have a keynote presentation after this, and then we have, I think, 6 presentations from our partners from Indonesia, from Malaysia, from China, from Russia, and from Philippines. So that will be our program until I think we plan to finish by 1 o'clock Malaysia time. Unfortunately, we have a very limited and short time, so we try to be realistic. So usually online programs can the best online program lasts only for 3 hours. More than that, it can be quite lengthy, and it's so hard to get you focused into it. So our keynote speakers we will allow like 5 minutes Q&A session, but for other presenters, if you have any questions, so you can put it in the chat area, and then of course we will allow you if you're very much involved with the research, so you can communicate with the scientists that going to present this morning. So we don't have any particular Q&A session for other presentations. For tomorrow, it is a dedicated session. So some of you who involved with research in upwelling in the region are very much invited. So it's a very dedicated session in the sense that tomorrow's session will be a discussion forum on how we're going to use this, on how the group will carry on our mission of producing knowledge in upwelling, and also disseminating our knowledge in many various ways. So we hope that through discussion tomorrow, we will reflect our plans according to the United Nations Decades of Ocean Science. So that will be our plan for tomorrow. So I hope most of you that have interest in the topics of upwelling will be able to join us tomorrow morning as well. So our next program will be our main presentation from our very special guest from Australia, Associate Professor Dr. Joshan Kampf. So he is now in Flinders University, working as an researcher in oceanography. So I think his contribution in upwelling studies is tremendous. I've been reading some of his works previously. The difference that we have is usually when we talk about upwelling system, lots of studies are focusing on large upwelling system like in Pacific Ocean or Atlantic Ocean and Indian Oceans. So you rarely find very dedicated works in marginal sea or small scale oceans. And in fact, our groups is basically focusing into that, which is seasonal upwelling, small scale upwellings, upwelling within the marginal seas, which is very much different from large scale upwelling. And I think one of the publication that Dr. Kampf have produced is quite which is quite important, which is edited books under the title of Upwelling System of the World. So I think this publication you can get it from Springer. I think there is ebook online if your institution subscribe to Springer ebook, so you can get the book online. So it gives you lots of explanation on many various types of upwelling from the big scale up to the small scale. So I think we can. I can't wait for this presentation, because I believe that the camp have lots of things to share with us this morning. So Dr. Camp, so I allow you to. So I share the floor with you, please.
Yes, thank you very much, Vasil. I'm happy to take over. Can you hear me? Is the sound good?
Perfectly.
Okay, sound is good. So let's get going. I slightly changed the title of my presentation to Upwelling in the Southeast Asian Seas, Where, How, and When. And I did not really know how to prepare myself for the meeting, but let's get started. So I wrote a book with a colleague, Piers Chapman, on upwelling systems in the world. And I always thought that the large upwelling systems like the California and the Peru upwelling system, that they are the most productive systems in the world in terms of fish production. But I wrote the book and in the end and looked at the fish production data, and it actually turned out that the South China Sea and surrounding seas are way more productive than all the other major upwelling systems. And I was very surprised by that. And I was also surprised to see how little is known about upwelling in the region. And I also did, after writing the book, actually did a little bit more research studies on that. So, okay, let's get started. How do I, okay. So content, I just want to give you some very, very basics of the upwelling of dissolved nutrients. Okay, some very basic, if you never heard about upwelling, some introduction. And then I actually, just using satellite images, is everything good with the sound?
Yes,
yeah?
yes, good.
Just want to highlight the key upwelling features in the region. And then I actually want to present something new, which has not been published, very fascinating stuff, actually associated with downwelling. Okay. All right. So very, very simple basics. Okay. So essentially near the surface in the oceans, we have a nutrient limitations. There's not enough dissolved nutrients available. Okay. In the so-called euphotic zone, okay, plenty of nutrients at depth. And at depth, we have a light limitation. Okay. So upwelling is a physical process that actually provides dissolved nutrients into the euphotic zone, and that kicks off photosynthesis and plankton production. Okay, and sometimes upwelling is related to a vertical velocity, but that can be misleading. You know, it's actually upwelling should be always, you should ask the question, upwelling of what? Upwelling of dissolved nutrients. So we're actually talking about a nutrient flux, an upward nutrient flux. Okay, so once you have that, it kicks off phytoplankton blooms and then feeds through the food chain, yeah, leading to higher zooplankton abundance and eventually feeding fish. Okay, so it's a simple theory of wind-driven coastal upwelling, and I'm not going too much into the details, but essentially what you need to have a coastal wind blowing along the shore in a particular direction. The coast has to be on the left with regard to the wind direction, as shown here in the top image. In this image, for a sufficiently long time, say for half a week or longer, okay? And what this does, it produces a cross-shelf circulation involving Ekman layers that actually brings up shelf bottom water to the surface, okay? And so without any nutrients, this process wouldn't do anything. But if you have the shelf bottom waters and dissolved nutrients, it then kicks off the marine food chain based on plankton blooms. Okay, so I just want to highlight that an important process is the so-called preconditioning, which means any process which actually lifts nutrient-rich water over the shelf break onto the shelf. That could be submarine shelf-incised canyons can do the trick in some regions, okay? Also noting here, there's a process called downwelling, and the downwelling process is more than just the opposite of upwelling. And I show you an example later on. Downwelling happens for the opposite wind direction. Okay, so now it takes a while before the pycnocline, the nutrient-rich water, reaches the surface. What you also can have in the ocean is a situation of subsurface plankton blooms, which are initiated by nutrient-rich water reaching into the euphotic zone, but not reaching the surface. There's a little sketch here at the bottom of that. And this is a process that is relatively little understood in many regions, because with satellites, you only see the surface chlorophyll concentrations, okay? All right, so now upwelling is a little bit more complicated than you think. It's not a purely regional process, and I try to produce this little sketch to illustrate what's happening. Yeah, just imagine you have sort of a coastline. Okay, you have a coastline and you have upwelling favorable wind blowing along the coastline, actually producing an upwelling center along this stretch of the coastline. What you also create, this feature actually creates a Kelvin wave that propagates away from the center. And I call this Kelvin wave tail. Kelvin waves can only propagate into one direction. And so you actually have something like a preconditioning process. There's some upwelling in the direction of the Kelvin wave propagation. Okay, and that's a very, very important. So it's not so trivial, the upwelling process. Also, Kelvin waves created upstream can also prevent the upwelling process. They can just stop it. Okay. Indeed. Okay. On the other side, the geostrophic flow, it's a so-called upwelling jet produced in interaction with something like a headland, can produce something that we call a turbulent wake. It's shown here in the sketch. Okay, here's the turbulent wake. And these turbulent wakes, they help to identify, in satellite image, you can identify the upwelling regions. I show you some examples as well. Okay. So now what I did over the weekend is, I wanted to show some new examples of upwelling in the region. So what I did is I looked at, this is my study region, okay? And I looked at some satellite images just to illustrate the upwelling regions for this talk. And what I did is also to include the Arafura Sea, okay, in the southern region, and also the regions along Sumatra and Java, because there are indeed, as many of you know, there are significant upwelling regions, okay? Okay, so east regions further to the north are not included. So now it's actually relatively easy what you do. You just look at the wind field. So this is from my book. Actually, if you want to have a cheap version, so I might have some free copies of this book. So if you want to learn about upwelling, just drop me an email. Email is on the first page of my presentation. Okay, if you're interested in having a copy of this book. Okay. So if you now look at the monsoon-related wind changes in the area, and there's just a maps for the summer time and for the winter time here on the left, you can actually see it's a relatively uniform wind fields, you might think, okay, but if you look at these sketches, you actually have a wind reversal, and you can now just applying this simple rule with that you need winds along the coast, you can actually produce a little bit of sketches of where do you expect upwelling to occur. Okay, and these are these red areas here. Okay, so now let's look into the real world. Okay, indeed, the details are far more complex. You can have very short-lived upwelling system, bathymetry interactions, and there is a relatively new review paper, and I give you the reference here, and et al. Review paper, and it's a really nice review paper of coastal upwelling research in the area. Okay, so now let's have a look. I'll give you one example. And what we do is we look at upwelling during the summer monsoon, boreal summer monsoon. And on the left side, I just show you the wind components, wind speed components, northward and eastward. It's a little bit confusing sometimes. Northward means really the wind going to the north, which means southerly wind component, and eastward is the wind that goes to the east. Okay, anyway, so you can produce little sketches, and it's shown here on the right-hand side are the sketches of the dominant wind directions. And I use a product which is called fluorescence line height, which is better than ocean color, because ocean color that many of you use, the chlorophyll A from ocean color, can be biased from sediment and other so-called yellow matter. Okay, so this is fluorescence line height on the right-hand side, and whatever is red has high concentrations, and blue and the gray areas are missing data due to cloud, and blue means essentially zero. Okay, so if you look at that situation, you can identify a number of significant large upwelling systems. Not talking about the small ones. These are monthly mean data, okay? Monthly mean data. And let's look what you can find. You can indeed find the large upwelling system along the Vietnam coast, okay? And this is just, you have the wind there producing offshore Ekman transport, sucking nutrient-rich water to the surface. And everybody knows about this system. The reason why I included the regions in the south are you also have the Sumatra-Java upwelling. The Sumatra upwelling develops in positive Indian Ocean dipole events, okay? And there is a majestic upwelling system in the Arafura Sea. So this is south of the equator. And we're talking about scales of up to 1,000 kilometers, okay, maybe 500 kilometers in this region, 5 by 300 kilometers. So this is absolutely massive, the upwelling in that region. Okay. What we also find indication it's not really reflected in the monthly mean wind is upwelling along the Chinese coast, indicated here. Okay, but you can also identify smaller upwelling system. Here's one that did you see? I just moved back one and look at what happens on the screen. Can you see this? This little upwelling, you think, or is there something? You have to go very close to the screen. Can you see something? No, what I did is I actually give you a little bit more detail on this. Have a look at that. This is how it looks like. Okay, during this time, South Sulawesian upwelling, and here you can see a classical turbulent wake. You can see the upwelling center, okay, and we're talking about a distance of 100 kilometers. So if you study an upwelling system, other seasonal upwelling system, this is also big. So don't fool yourself. This is not a tiny upwelling system. This is a super big upwelling system. Okay. So now just going back and not going back, I go now to a different time. So this is all sort of expected. You know, there maybe some surprises in here. Now I go to December. Okay, looking at December. The winds have reversed. You can check that with wind fields or so. These white arrows on the right-hand side show you the wind fields here, okay? Reversed, but you still get significant signals in fluorescence line height. Okay, how does this work? So everything you learned now about upwelling doesn't work any longer, because you actually get a downwelling favorable wind. And we know from the currents that you get very, very strong frontal flows along the coastlines here of China and of Vietnam. Sorry, I always get here notes that I have to admit people from the waiting room. So it's very tricky for me to do this presentation. For some reason, I'm sort of the administrator for that. Anyway, okay, so now you're confused. This is not the right wind. So what are we doing? Okay. And I want to talk a little bit more. So no, first of all, this is a time series now along just Vietnam coastal waters. Fluorescence line height, you can do something the same with the ocean color, and over 10 years. So you get 10 years of data, and you can identify the plankton blooms triggered by the summer monsoon. Okay, these ones are the red circles here. Every year, very, very robust feature, because every year you get the upwelling promoting winds and upwelling. However, you get secondary peaks, and sometimes in December, yeah, this just before, sometimes a little bit weaker, sometimes a little bit later, many times in December. Okay. These are every year, I go back one slide, everywhere you get this feature. Okay. And I don't think it's river influences. I don't think it's river influences, because you would expect some other another feature. So what is it? Okay. So let's see, how much time do I have left? I think I'm good with the time, am I?
Yeah. 10
okay.
minutes.
10 minutes is good. So timing is perfect. So just a little bit more scientific details. What actually happens during coastal upwelling? What happens during coastal downwelling? Just illustrated with a computer model. Okay, so it's a computer model that is, it only shows a vertical slice shown here in this image. The water is only 100 meters deep, and it has stratification, density stratification. Blue is light water sitting over, there's some pycnocline, density changes here, and red is a heavier water. And then the model is forced by prescribing wind along the coast. Okay, you could produce either upwelling or you create downwelling. Okay, here's the reference to this publication. Okay, and you will understand what I mean in a minute. What is the significance of this discussion? So first of all, I show you what happens during upwelling. Okay, you have upwelling, and here you have 4 panels on the left. Shows you the results after 5 days. 5 days of simulation. The top panel shows you the density field. Red is heavy water, and you can see that the red water has moved to the coast and into the euphotic zone to the surface. Again, you can see that the blue water has retreated from the coast. Okay, this is coastal upwelling. The second panel shows you the onshore, offshore circulation in the ocean. You see the Ekman layers. You see near the bottom, a bottom Ekman layer, the blue, something, yeah. And, oh, sorry, moving back. And you can see offshore Ekman transport near the surface. The important detail here is upwelling extends into very, very shallow water. So you move the upwelling, the near bottom water is moved almost to the shore, to the coast. Okay. The third panel shows you the alongshore circulation. You can see the upwelling jet here. This red thing is an upwelling jet, and for longer events, it actually will move away from the coast, but still the Ekman layers, the bottom Ekman layer reaches very, very close to the coast. It's a very important feature. Okay. It also means that the near coastal water can remain relatively stagnant. The upwelling jet is actually next to it. Very important here. So if you think in terms of friction with the seafloor, because it remains stratified, it reduces the turbulence and there's very little friction with the seafloor. I show you some a distribution of the bed shear stress. It remains relatively low. What it means is that anything that you produce in terms of the detritus, the dead organic matter, tends to settle or onto the floor and can accumulate on the seafloor. So now comes the surprising other feature, downwelling. So what happens if you have downwelling? I'll show you downwelling. The wind is reversed, and you can see during downwelling, the blue water, the surface water is pushed against the coast and then downward and creates a front near the bottom. This is downwelling. So now there's two significant features happening during downwelling. One, and this is observed, okay? So it's only illustrated here. One is that the cross-shelf circulation shuts off near the shore. You can see here it's all green. Okay, it all mixes essentially, it all disappears. This one has no little onshore, offshore. The other feature that happens is you create a downwelling jet, which is the blue jet here, this blue region. This is the downwelling jet, but it becomes mixed very close to the bottom and you produce a significant, a very high friction with the seafloor, a very high shear stress. And these shear stresses are called extreme bed shear stresses and can exceed 0.4 of a Pascal. And they are so strong that there is no problem of eroding sediment and actually releasing the nutrients from the sediments. Okay, so what downwelling does is it removes stratification near the coast. You can see it removes here, it's all blue. And it creates a zone with very high shear stresses. And this zone over time actually moves from the coast up to distances of 5 to 10 kilometers away from the coast. Okay, and stirs up the bed sediment. And what I'm saying, this one is you know, that's the link to what I think happens during the winter monsoon with the downwelling favorable winds actually releasing all the nutrients that come from the seafloor. So I'm very excited about this. Okay, so now the other features, indeed, and many you will hear about this in subsequent talks, is if you zoom in on smaller scales. I gave you one example before, but here you can see more. This is, for example, December 2019, and this is an already reported upwelling system here in the northern coastline of the Philippines. And you can see also Philippines has many different coastline orientations. So technically you can have upwelling at any time for any wind direction. Okay. On the right-hand side, February 2020, there's a massive upwelling here on the southern margin of the Sulu Sea. And look at that, it's over a distance of 500 kilometers. So there's probably many things that we still have to study. So summary, monsoonal winds create various large seasonal coastal upwelling systems, and I only focused on the large ones in Southeast Asian seas. Probably some upwelling systems have not been scientifically documented. You know, I mean, studied, most of them have not been thoroughly studied, but some might not have been reported. And I postulate that the downwelling mechanism is very, very important to create plankton bloom as well. So if in your study, I encourage you to look at downwelling features. And I hope that I managed to stick to the time. And if you have questions, I'm happy to hear them. Thank you very much.
Thank you very much, Dr. Kempf. it's a very interesting presentation, I must say, because I think your summary reflects the whole presentation very well, because I think our area is very much defined by monsoon seasons, and monsoon somehow give a lots of varieties of dynamics to the system. And then when you talk about downwelling, I never thought that downwelling can be such an important interesting features, because not many people study downwelling because of its lacking in terms of productivities and whatnot. But I mean, this your papers in about downwelling on the bed shear stress is something new that I think later on lots of people that are working in a small scale outwelling, especially in the near coast outwelling, must I think it's a good prospect to have a look at downwelling more than we ever thought before.
But it only works if you have upwelling, because you need to have the nutrient load on the floor in order to create it. You might be excited and say, oh, there's downwelling, but nothing happens.
Yeah, if I can understand, it's so the previous season upwelling, and those upwelling nutrients is the one that's gonna benefit from those downwelling in those particular areas. So very interesting. I open up for a few questions. We have 5 minutes for question and answer. You can put up in the chat area. I have one question from Dr. Niguez Aleta. So very interesting presentation. Thank you. I'd like to ask if the downwelling driven blooms work only for particular depth. Do you have any answer for that?
Depth?
Yeah. Is it shallow or deep area? Can it work in?
No. It's essentially from the coast, and then I don't know how far offshore, because here the downwelling winds exist for a long time. I don't know what the limit is, but I would think it can go to 10, 20 kilometers. And you can see that the plumes in the picture that I showed you, the width of these areas are significant. Okay, but more important is probably that you have to mix the entire water from the bottom to the surface. If you only mix near the bottom, then the sediments then the nutrients they don't reach the surface. That might be, but
yeah.
I don't know. I'm waiting for any confirmation, because this one is sort of, I couldn't believe my eyes when I this is from the last weekend, essentially. I tried some regions, but it's pretty apparent for me anyway.
All right. I have one question from Dr. Agus from Indonesia. So he asked about the interaction between classical Ekman upwelling system and region current systems. Do you have any comment about that?
The classical upwelling system and the regional currents are directly related to each other, because upwelling creates these upwelling jets, downwelling creates downwelling jets, and these are essentially the coastal currents that you see in the area. If I understand the question right.
Okay, there's one. Okay, I think I can have one more question here. Dr. Lim Potin asking whether can you comment similar upwelling or downwelling features, if there is any, along the Malacca Strait. Have you gone through to that area, Dr. Kamp?
I am aware of this region, but I never. I always looked for actually real chlorophyll measurements as a confirmation of the satellite data that you get. And I'm it's relatively narrow. And so I'm really a little bit reluctant to make any interpretations in this area. It's very, very interesting, but you need to have.
If I can just tell you that if you have worked before in any area with a very strong tidal currents, because Malacca Strait is known for a dominant tidal current system.
Okay. Look, what you always need to create a plankton bloom is you need to have a sudden release of nutrients. So if you have it mixing all the time, I'm not sure how long would it take for the nutrients to be You need that source of nutrients. It just will be used up. You have your mixing, but where is your source? You always have to think about where do the nutrients come from. I mean, that indeed they can come from the rivers and then the tides, but I think the question about the source is always the important one. Where is the nutrient source?
Yeah. All right. I think I can take the last question if you can read from the chat. So it's about the turbulent wakes show up if Kelvin wave become untrapped near strong coastal curvature.
Oh, I don't know. I will answer more questions that I get just looking. I can't read this question. You know, I promise that I do that in the next. I will stay online and I will just try to answer questions per text.
All right.
I don't
Thank
have
you
to
very
make
much.
it so long. Okay.
Yeah.
Thank you.
All right. Thank you, Dr. Cam, for your kind presentation, because I think we are very I think thankful to have you here with our groups this morning. All right, I will send this. Dr. Zoraini will continue this session, so she will introduce all our presenter this morning. So, ready?
Okay. Thank you, Dr. Fazil. So, for your information, just want to let everyone know. So, currently we have previously we have 102 participants. Now we had left with 97 participants. So, but it's still a good news to us. So without further ado, for the presentations, the first presenter I would like to call Prof. Ishaq with his presentation titled Seasonal and Interannual Variations of Surface Chlorophyll A in the Karimata Straits. Please, Prof.
Thank you. Can you hear my voice?
Yes, yes. All right.
Can you see my slide?
All right.
Okay, thank you. Thank you, Prof. Fazil, for the invitation to this workshop. So also to the WESTPAC for organizing this workshop. As Prof. Fazil said before that this is initially will be conducted offline in Palembang in South Sumatra, but due to the COVID, we cannot organize the offline conference. So today, I would like to talk about the surface chlorophyll A variability in the Karimata Strait. This work is with my former students, Kurnia. She's in the University of Pajajaran, and Dr. Eko from Jamstek, and Prof. Izizaka from Nagoya University. So my talk will be organized as it is. So we have, I start from the motivation and objective, and then I show the data and method that I use to show the variability of the surface chlorophyll A in the Karimata Strait, and in terms of seasonal and interannual variation. And the last one is summary and conclusion. So I would like to start my presentation with this. So this is the pattern of the surface circulation within the Indonesian Sea and the adjacent sea. So we can see that there is a very complex surface circulation within the Indonesian Sea and then the outer sea. In particular, we can see that the Indonesian Sea is a low latitude crossroad of the water mass from the Pacific Ocean, and also from the South China Sea, and then from the Indonesian Sea. So this water is made within the Indonesian Sea, particularly in the eastern Indonesian seas. And also the Indonesian Sea is the link of the tropical ocean between the Pacific and the Indian Ocean, so-called the Indonesian through flow. And our studies will be focusing on this area. This is the Karimata Strait. So the strait that link between the South China Sea and the Java Sea. So the previous study have shown that the Karimata Strait is part of the branch of the Indonesian through flow, in which the water from the Pacific water is coming to the Indonesian Sea through the Karimata Strait and flow southward into the Java Sea before they return to the Pacific Ocean through the Makassar Strait. But this water from the South China Sea is the surface layer, which is a very fresh water, and plug into the Makassar Strait, and this caused the the decrease of the surface transport in the Makassar Strait, and this surface circulation has also a strong interannual variability associated with the ENSO, and also this surface water from the Karimata Strait and will alter the meridional velocity in the Makassar Strait, in particular in the upper layer. Another thing is that the South China Sea also shown that to influence to affect the Indonesian through flow in the Makassar and in the Karimata Strait, and then from the observation, it's showing that the annual Karimata Strait through flow is about 0.5 spectra toward the Java Sea. So it's from the South China Sea toward the Java Sea. The South China Sea transport also indicates the interannual variability associated with the ENSO. It is strong during the La Nina, and it's weak during the El Nino event due to the pressure gradient between the Western Pacific and Eastern Pacific, and cause the change in the surface circulation. And in seasonal variation for the surface current and sea surface high also very clear difference between the boreal winter in December, January, February in the upper left figure, and boreal summer in June, July, August in the lower left figure. So during the southeast monsoon, during boreal summer in June, July, August, the wind is blowing to the from the south to the north, or from the southeast to the northwest. Wind blowing over the Java Sea and the Karimata Strait, and this is caused the upwelling that lead to the northwestward surface current and a low sea surface high in the Karimata Strait. But during the boreal winter in the December, January, February, and during the northwest monsoon, so the situation is reverse, in which there is a northwest and southeastward current, very clear southeastward current in the Karimata Strait, and then high sea surface high in the Karimata Strait also is associated with the downwelling. And furthermore, the study about the chlorophyll A in the Indonesian seas during boreal winter. So during the peak of the Madden-Julian oscillation, during the peak MGO, we have a very high precipitation over the maritime continent, and also this is occurring in the December, January, February season in boreal winter, so that the surface wind is blowing from the north to the south, and cause the southeastward current in the Indonesian seas, and this high precipitation enhance phytoplankton biomass in the maritime continent. You can see that very high phytoplankton in the Karimata Strait and Java Sea, and then even further eastward in the Banda Sea. So it is suggested that the high precipitation associated with the active MGO event cause the enhanced phytoplankton biomass in the maritime continent. So given the importance of this variability of the phytoplankton biomass in the Indonesian Sea, we then try to explore the seasonal variability of the observed surface chlorophyll A in the Kalimantan Strait and evaluate possible influence of El Nino and La Nina on the spatial distribution of the surface chlorophyll A in the Kalimantan Strait. So this is the data we use. We use the MODIS data for the surface chlorophyll A, and the surface wind is from the ECMWF, and precipitation also from ECMWF. And then SST is from the optimum metropolitan SST from NOAA. So the period of study is from 2003 to 2015. So this is the seasonal variability of the surface chlorophyll A during the northwest monsoon in December, January, February. We have a very high chlorophyll A concentration in the Kalimantan Strait. It's in contrast with the South Java area. So in the south and southern coast of Java and Sumatra, during the northwest monsoon in December, January, February, we have a low surface chlorophyll A. But in Kalimantan Strait, we have high chlorophyll A during the northwest monsoon in December, January, February. If we look at the SST and the surface wind, we can see that very strong northwest monsoonal wind blowing of the Kalimantan Strait from December until March. And this is associated with the low sea surface temperature. And this low sea surface temperature seems to be affected from the South China Sea to the Makassar Strait. And the wind is weakened in April and then reverse direction in May. And the strong northwest wind is caused the upwelling here, and if we can see the wind stress curve, and the positive mean the upwelling for the northern hemisphere, and the negative mean the downwelling for the northern hemisphere. And we can see that during December, January, February, in the northern hemisphere, we observe very high positive wind stress currents associated with the upwelling, and in the north of the Java Sea, we show the negative wind stress curve, and because this in the southern hemisphere is caused the upwelling here. And this location of the high positive wind stress curve in the northern hemisphere and the negative wind stress curve in the southern hemisphere is correlated with the high surface chlorophyll A variability in the Kalimantan Strait. But this wind only could not explain all the variability of the surface chlorophyll A during the northwest monsoon season. And as previous studies suggested that the precipitation may enhance the phytoplankton biomass in the Kalimantan Strait during the northwest monsoon season. And we look at the precipitation, then we can find that the high precipitation occurring in December, January, and February also possible source of the phytoplankton from the river in the Sumatra Island and also in the Kalimantan. So the combination of the upwelling driven wind and also the high precipitation in the maritime continent caused the high chlorophyll A concentration during the northwest monsoon season in Kalimantan Strait. And we look at the southeast monsoon season in June, July, August. We have high chlorophyll A variability in the Kalimantan Strait, and it's more wider area in the Kalimantan Strait. And if we look at the wind, and we see the southeast, I mean the northwestward wind or southeasterly wind is blowing in the Kalimantan Strait and Java Sea, and this caused the upwelling, and this strong from June until September. And also we found the northwestward intrusion of the cold water from the Java Sea into the Kalimantan Strait, even to the South China Sea. And if you look at the wind stress curve, we can see that the negative is caused downwelling, but in the southern hemisphere, the positive here is indicate the downwelling of the event. So in the here in the south of the Kalimantan, we can see high negative wind stress score, and it's associated with the strong upwelling and cause the high chlorophyll A variability in the Karimata Strait. And precipitation showing the low precipitation observed during the southeast monsoon, and these also make indicate that the precipitation do not play a role in the high chlorophyll concentration during the southeast monsoon in June, July in the Karimata State. And finally, the interannual variability, we look at 2 El Nino event and 3 La Nina event, and this is the left side is for the La Nina El Nino years, and this is the right side is for the La Nina years. The upper panel is for the chlorophyll, the middle panel is for the wind and the surface temperature, and the lower panel is for the precipitation. And we found that during La Nina year, when we have a high precipitation over the maritime continent, we have very high chlorophyll A concentration in June, August, September year. And in El Nino year, we have strong or high chlorophyll A concentration, I mean, in December, January, February, when the precipitation is already high in the maritime continent. And we can conclude that during December, January, February in El Nino year, and in June, July, August in La Nina year, high precipitation over the land that cause increase of nutrient from the land through the several river discharge, and it's lead to the high chlorophyll A concentration in the Karimata Strait. So this is the summary. So we found that the chlorophyll A concentration in the Karimata Strait reveals strong seasonal variability, and also strong interannual variability. In which during La Nina year, observe high precipitation in June, July, August season cause an increased nutrient discharge that lead to the high chlorophyll A concentration observed in the Karimata Strait. And similar situation was observed in December, January, February season during El Nino years. I think I stop here. Thank you.
Okay, thank you, Prof. Is there any questions? So you can just type in the chat session.
And we hope that the Prof can answer in the chat.
Okay, and we hope maybe you can just type your questions in the chat, and then Prof Ishak will answer it in the chat too. So
okay.
I think we continue with the next presenter, shall we? So the next presenter.
Thank you.
All right, thank you, Prof. So the next presenter will present about the upwelling dynamics in southern South China Sea and impacts of El Nino. So I will, without further ado, we invite Dr. Ernest Koch.
Yeah, good morning, everyone. Can you guys see my screen?
Yes, Koch, yes.
All right. Okay, so, okay, good morning, good afternoon, or even good evening to everyone of you, no matter where you are. Yeah, I am Bohen Koch, as actually I am from the Institute of Oceanography and Environment, University of Malaysia, Terengganu. So today I will like to share a little bit about my research, which is the upwelling system, which is located in the southern South China Sea, which is particularly located along the east coast of Peninsula Malaysia. All right, so first of all, I would like to provide some of the basic introductions about the South China Sea. So as we know, the South China Sea is dominated by the East Asian monsoon system, whereby during the boreal winter, the South China Sea is dominated by the northeast monsoon. However, during the boreal summer, the southwest monsoons is dominated, prevail over the South China Sea. So actually, the different wind configuration during these two types of monsoon season generate the upwelling in many of the locations in the South China Sea, which is highlighted in the red circle here. So actually the east coast of Peninsula Malaysia is located in the southwestern part of South China Sea, and eventually the upwelling season is during the southwest monsoon. So I would like to share a little bit about how we discover the upwelling features. For information, the upwellings along the east coast of Peninsula Malaysia is just only be discovered after the 21st century. So during the hydrographic observations, we actually discover very interesting features whereby we can observe that there is a domo highlight uplifting as presented by this figure. This figure is showing the isoline of temperature and salinity is showing towards the coast and surface, which is the classical idea of the upwelling. So this is just showing the example during the southwest monsoon. So after confirming these features, we try to do the further analysis by looking at the sea surface temperature derived from the satellite. So this is showing that along the east coast of Peninsula Malaysia, there's a cooler water band formed along the east coast of Peninsula Malaysia, which indicate that the upwelling does not only occur on the specific location, however, it occur along the entire the coastline of the east coast of Peninsula Malaysia, from the southern tip of the coast and stretching until about the 5 degree knots. So which is considered as a large scale also, right? So after confirming there's a presence of the upwellings along the Peninsula Malaysia east coast, we try to look at what actually the factor causing the coastal upwelling along the east coast of Peninsula Malaysia. So we try to look at we try to focus on the wind driven upwelling process, which is focusing on the ammonia transport and ammonia pumping. So because these two processes is considered as a major upwelling driven mechanism is in the world oceans. So this graph, this map showing the ammonia transport. So we can see that the ammonia transport is directed offshore. So it actually creating the surface divergence on ocean surface, and hence the upwellings happens. So another point of view is from the ammonia pumping. So we can see that along the east coast of Peninsula Malaysia is covered by the positive value of the ammonia pumping. So which is categorized by the circular wind, and this circular wind actually generate the ocean surface divergence, which is favorable for upwelling. So we can conclude that both of the ammonia transfer and ammonia pumping is actually playing the very predominant roles in the upwelling driven process along the east coast of Peninsula Malaysia. So now we are trying to look at, is it the upwelling along the east coast of Peninsula Malaysia is actually coming into the inter-annual variability or not. So we try to conduct the empirical orthogonal function analysis, so to determine the inter-annual variations of upwelling along the east coast of Peninsula Malaysia. So this is the percentage variance. So you can see that the EOF Mod 1, so it's actually having the very high percentage variance, which is about 81%. Okay. So in order to determine the noveltiness of the EOF mode, we do the Monte Carlo randomization test, and it is suggested that the cutoff point is at the EOF mode 1. So the reason on why we conducted the Monte Carlo randomization test is that we want to determine the 0.05 significant level. So So in our study, we just consider EOF mode 1 only. And this is the map showing the routing map of the EOF mode 1. So we can see that there's a curve of two zones, so which is represented by the Z1 and Z2. So the Z1 is representing the outwelling water, cooler outwelling water that formed by upwelling in the inshore region, whereas the Z2 is representing the slightly warmer offshore water, right? So in order to answer why there is inter-annual variations on the upwelling, so we try to look at the wind stress anomaly and also the wind stress curve, and we actually conducted a present correlation coefficient analysis test. So we can see that the alongshore wind stress anomaly is actually very is having a very high of correlation coefficients of 0.71, so which indicate that the Alonso wind stress variability is imperative to induce the interannual variations of Upwelling rather than the wind stress curve variability. So which means that the Alonso wind stress anomaly is important in the generation of the interannual variations of Upwelling along the east coast of Peninsula Glacier. So we want to know what actually causing the interannual variations. We try to relate it with the ENSO event, which is we compare it with the multivariate ENSO index, all right? So this is a graph of MAC index and also the EF-1 time series. So the dashed line, right? So in our previous study, there's two strongest Upwelling event in the study of in the period of study, which is during 2009 and 10, and another one is 2015 and 16. Okay, so this is the strongest, two of the stronger Upwelling. So as we can observe from the F time series, the Upwellings in these two particular lines is these two particular years, is weakest in 2010 and 16, which indicate that the El Nino slackened Upwelling in the subsequent year of El Nino, which is as a result of the delay ENSO effect. So we make a hypothesis. So indicate that delay ENSO impact is actually causing the interannual variation of the Upwelling. So we try to do the further analysis by doing the present correlation coefficient analysis between the multivariate ENSO index with the time series of AF-1. So we can see that the AF-1 was actually very highly correlated with the multivariate ENSO index 3 to 12 months ahead of the AF-1. So with the higher correlations is occur at the time of 6 month lag. So which indicate that our hypothesis is true, which is indicate that the delay ENSO impact is actually causing the interannual variability of Upwelling along our regions. So we come back again to this map. So we can see that the El Nino during 2015 and 16 is the strongest El Nino. However, the Upwellings as indicated by the AF-1 is not the weakest in this year. However, it's during this particular year, which is during the 2009 and 10s. So which considering that the strength of El Nino was not the factor in the determinations of the strength of Upwelling. So in our next study, we try to focus on these two particular years, which is 2010 and 2016, to look at what actually happens within these two particular years. So we conduct the further analysis, so focusing on these two particular years. So, and we can see that the elongated polar water band that formed by Upwelling during the 2010 is almost disappear if compared to 2016, which indicate the Upwelling during 2010 is much weaker if compared to 2016. So in order to explain why actually causing this situation, what is the factor causing the Upwelling to be weakened, so we do the analysis on the wind stress anomaly and also the wind stress anomaly, the shaded in one. Okay, so we can see that during this two particular year, so the wind stress anomaly during these 2 years is actually suppressing our Upwellings. But during the 2010, the wind stress anomaly, the intensity of wind stress anomaly in 2010 is much higher, which is explain why the Upwelling during the 2010 is much weaker, right? So from another point of view, so we try to look at the wind stress curve anomaly during 2010. So we can see that the wind stress curve anomaly in this 2010 is much weaker if compared to the 2016. So which again suggested that the weakening of the wind stress curve anomaly also causing the Upwelling intensity in 2010 is weaker than the 2016. All right. So we always try to look at the large pictures. We do the analysis by correlate it with the wind vector anomaly located in the between the Pacific and Indian Oceans. So we can see that during the year of 2010, there's a formation zone Northwest Pacific anticyclone anomaly wind, which is formed by the Indian Ocean capacitor effect. So in addition to this, there's a northerly winds that prevail from the subtropical Western Pacific Oceans. With this assistance of these two winds, play the important role to weaken the upwelling in this particular year. But what actually causing the upwelling in 2016 to be weaker? So we can see that during this particular year, there is a formation of seashore winds, okay, in this year, all right? So this is actually engendered by the SST warming enhanced convection of the Southeast Tropical Indian Oceans, which is played the important role to weaken upwelling. So the conditions, so we can conclude that the conditions that generated during 2010 is played the important roles to weaken the upwelling rather than 2016, which as we only have the seashore wind. So this explains why the upwelling during this 2010 is much weaker if compared to 2016, right? So I have done the first part of my presentations. Now we actually conducted a modeling study in the Indian Oceans and also the Pacific Oceans. So we actually run the numerical model, run the numerical simulations by using the regional oceans modeling system, which is ROMS. So we actually doing the hindcast mode, and the simulation is conducted within the time of 2000 until 2018. So the simulation is occupied about the 19 years. So this is the model domain. So our model resolutions is about 5 to 6 km. Yeah, it's actually 5 to 6 km with the vertical resolutions of 30 sigma level. So this numerical simulations is conducted under the cooperations between the University Simulation Terengganu and also the University of Western Australia by using the super HPC high performance computing system, which is located in the PAUSI super computing system. So I would like to show some of the result of these simulations. So this is the sea surface temperatures during the DJF, which is during the boreal winter, the December, January, and February. So we try to look at this video, right? So we can observe some of the upwelling features through the simulations. So there's a, so I hope that everyone can focus on the cooler water regions. So we will show in this map. So I now bring this video. All right. So this is during the northeast monsoon during the boreal winter. So during these two particular time, so there's upwelling occur in the northern part of the Indian Oceans and in the Indonesian regions. And beside of this, there's also upwelling in the northeast of Sabah, the Philippines Islands, and also the Luzon Strait. Okay, so there's we can see from this model, there's we still able to observe some of the upwelling locations, right? So yeah, there's a very clear of cooler water here in this region and also the Luzons, right? So now we focusing on the for the boreal summer, which is during the southwest monsoons. Okay, so this is simulation showing the SST during the June, July, August, and also September. Okay, so try to focus on the cooler regions, cooler SST regions. All right. So okay, so you can see that the cooler water is developing here, it's happened here, the upwelling, and also we can find the upwelling location along the east coast of Peninsula Indonesia, the Jawa Sumatra regions, the Sulawesi, the Banda, and some of the this region. So I'm not sure whether it's upwelling or not. So so through our simulations, we can conclude that the simulations, our simulation is actually can be used to study the upwelling features along the which covered by this domain. So I hope that if you guys interested in this data set, we hope that you can always contact us regarding the data. Regarding this data set, we actually have conducted simulations of the temperature salinity the UV current vector and also the sea surface height. So if you want to obtain this data, you can always contacting me or either Dr. Fazil from INOS. So we are happy to share, and in the future, we hope that we can work together to study the Upwelling region, which is have not been discovered in the past. Okay, so I guess this is end of my 3 presentations. So thank you.
Okay, thank you, Dr. Kok. Just a note to Prof. Ishak. There's a question for you in the chat. And also for Dr. Ernest Kok. So we hope that you can answer in the chat. Okay.
Yeah, okay, sure.
So,
Yeah, sure.
okay, so we would like to continue with the next presenter, Prof. Dong Xiao Wang, with the title of Coastal Upwelling in the Northern South China Sea. So, Prof, you are welcome.
Can you see my PPT?
Yes, yes.
Great. Hello, everybody. Good afternoon. My name is Dong Xiang Wang from Sun Yat-sen University. This work is done mostly with my team members, such as Ye Changshu from South China Sea Institute of Oceanography, where I worked over 2 decades before. So try to deliver a brief introduction about the dynamics of coastal warring in northern South China Sea. Actually, coastal warring mainly we can classify into 2 groups. First is the kind of, we said, wind-driven coastal warring. The mechanism is very obvious. If the wind is warring favorable, I mean along coastal wind, and there will induce a very strong offshore surface transport. This kind of surface transport can build a cross-shear pressure gradient, and this gradient enhance the along-shore current at the subsurface. And meanwhile, the near-bottom aquatic transporter will also favorite the coastal warring, like the diagram show you in the picture. And another way, if the wind could not support the warring, we call the topography induced warring. This picture in the left is provided by Peter Ocker from Australia. They call this topography induced warring because there's some kind of dynamics. But he mentioned if the topography is just a 2-dimension, I mean the z or x not change with y, then could not sustain for a long time, because geostrophic accumulation will enhance the very strong summer wind dynamics, will kill the coastal warring. If the topography is like a right planar, it's 3-dimension, I mean change with the x and the y simultaneously, that actually we call the narrow the shear or widen the shear. So the bottom fraction can enhance in just the 3-dimension topography, and their geostrophic balance will be disturbed. So later, most of my work want to detect how the 3-dimension topography works for the coastal warring in the northern South China Sea for some time. Okay, this is the diagram for the northern South China Sea. In the right panel, you can see mostly we assume the southern west wind is a monsoon wind prevailing in this area. And the snapshot is for the sea surface temperature. The low sea surface temperature in the east Guangdong coast is indicated for strong coastal warring. And meanwhile, if you take a look at the topography picture in the left panel, you do see this kind of a change with orography. We call it 2-dimension, 3-dimension both. And also there's a very strong interaction between the coastal current system and the interior South China Sea circulation system. So now we are thinking about, can we have a second resort for the coastal warring in the northern South China Sea? We said yes, because let's see the 4 cruise data. This is cruise data happening in 2000, 2005, 2009, 2011. 4 kind of a cruise show you even the wind is not a strong, very favorable. Actually, sometime for year 2005, year 2009, or even years of 2011, the downwarding favorable wind. Okay, but if you go to the transect of salinity, upwind is temperature and the low wind is salinity. Let me have some point. Can we have a point? Yes. Okay. So you do see the cold salt water intrusion to the shelf and become very strong warring phenomena, given the wind is downwind favorable. So we are looking for the mechanism. It's kind of the 3-dimensional topography has the induced warring happening in the northern South China Sea, and we're using some kind of mechanism and the model. First, we're using palm model to detect the whole picture. We designed 4 kind of experiment, and compared to the controller, we have a second for the no wind, and but with the latitude circulation or larger scale circulation, and a third one we without surface wind, but we also reduce the boundary current, and last one is we enhance the latitude condition. So we try to enhance how the larger scale circulation, particularly for the bottom layer, can matter for the maintain the coastal warring in the northern South China Sea. Now I show you the sea surface temperature. I pick up the day 13, so you can see, yeah, in the control run, we call the normal case. Yeah, you do see the low sea surface temperature happen quite strong, and but if compared to the control run, experiment 2, 3, 4, also number 2 and number 4 do, exact strong coastal warring. Even the wind is not strong or disappear. But when the wind and the latitude boundary current is disappear, number 3 show you very, very weak coastal warring. That means regarding the experiment 2 and 4, we can say there happen a very strong 3-dimensional topographic induced warring. And the reason is we needed to go to the vertical velocity. We compare the vertical velocity number experiment 1 and experiment 2, and the ratio between the experiment 2 and the experiment 1. And I just want to ask you to pay attention in the low panel of the right. You can see the some kind of the value of the ratio goes to 1. That means even the wind is disappear, given the strong boundary current, the coastal warring still happen over those areas. And the interesting things, we do check the bottom fraction and the bottom correction curve. You can see the bottom fraction could not explain it very well, because we found that the region of larger warring and the region of the high bottom stress is not coincident. It's kind of the different. So, but if you go to the bottom fraction curve, the really can match very well to this the control run. So the reason is we show you the dynamics like this. We assume the F plane. We have the potential vorticity equation, and if you do such integrate, we can do find that without wind forcing, we have a two term balance each other. First thing is a bottom Ackermann transport and bottom Ackermann pumping. So one is vertical, one is horizontal. So let's check with the picture. So we have the evolution change with the transect along the 13-meter S-bar, experiment 1, and along 15-meter bar, and along this is experiment 2, respectively. So you can see somehow in those two areas, the vertical and horizontal term balance each other. It's kind of the cancel each other. But over here and over here, that is like kind of the in some way. I mean, the both favorite of the coastal marine. So that is very simple dynamics for the why the three-dimensional topography can induce a marine in North South China Sea, just not along the whole coastline of the Guangdong coastal. It just happened in some particular area when the three-dimensional dynamics happen. And this kind of the phenomena can explain the interannual variability. I showed the picture for satellite temperature image from 2002 to 2016. I say we published a couple of paper to explain the interannual variability of large circulation in South China Sea really contribute or control the interannual variability of the marine intensity in this area. So it's kind of very big change, because before we said this is kind of summer monsoon preview area. It usually upwelling favor the wind happen, right? But if you goes through each year, you do find some year or sometime always downwelling favorable wind happen in Northern China Sea. And because of the large scale circulation in the bottom layer, the coastal marine still happen. So thanks to this mechanism, it's give a bigger fish resource for the coastal people in Guangdong or in South China. Let me summarize. First of all, three-dimensional induced upwelling is very important for the intensity coastal upwelling, and we check such kind of is much important for the wind-driven mechanism. And the second, the reason is because of wind shift, and the wind shift change with the direction along coast, and the horizontal and the vertical motion when the balance then disappear in some area. When it's invest, then it's enhanced the coastal marine. So I stop here for question or suggestion.
Okay, thank you so much, Prof. Dong Xiao Wang. If you have any question, just put it in the chat and Prof will answer it in the chat also. So we proceed with the next presenter. I'm sorry, I have a trouble to pronounce your name. So by Dr. Labanov, with his title is Primordial Upwelling System in the Northwestern Japan Sea. The floor is yours. Thank you.
Okay, thank you very much. Can you hear me?
Yes.
Yes, then I have to start my presentation. So I will talk about this primordial upwelling system, which is occurred in the northwestern part of the Japan Sea. And this is, I'm Vyacheslav Labanov from VI Lichov Pacific Oceanological Institute, which belongs to Far Eastern branch of Russian Academy of Sciences and located in Vladivostok. And there are contributors from my institute, Dr. Alexander Sergeyev, Pavel Tichenko, Vladimir Zvolinsky, Kaplunenko, Svetlana Ladichenko, and Evgenia Marina. And I will talk first about the geography of this area, because it's very important to understand the particular phenomena of this upwelling. And this is a seasonal wind-induced upfilling and as a regional part, but however, this is also mesoscale structure, which happen, local upfillings happen all season. And I will talk about the observations. This mostly observational presentation, observations of changes of oceanographic structure, primary production, and importance of the upfilling, this ventilation of the shelf area, especially the Peters Great Bay, which is elongated bay on the shelf. And I will talk briefly about our current work. And as I said, this is a seasonal wind-induced upfilling. When we look to the area, this is a Japan Sea, and Vladivostok is located here. And we have this is very deep basin, and this very steep slope here from 100 meters down to 3,000 meters is like a wall. And we have a long slope current, which call Liman current, or we call it in Russia Primorye current, because this region of Russia we call Primorsky Krai or Primorye region. And of course, there are kind of waves like Kelvin waves or topographic Rossby waves, like kind of marginal waves. And there's instability and current shear, so which produce local upwellings here. And we have monsoon wind. In winter, like now, we have northern winds. And in summer, we have southern winds. But there is a transition period in September, October, early November. We have winds from the west, which are favorable to generate upwelling in this area. And this is some satellite images shows, this is a SST temperature, and this is cold water here, and the warm water is here. And again, this is vice versa. The black is a more detailed image from the Landsat. This is, you see, the detailed structure of this upwelling area, which consists of sub-mesoscale features, with this cold water on the capes and this warm water in here. And this is an example of one of our survey, the ship-based observations. You see these upwelling in temperature. Of course, there's a cold water and differences about the 4 degrees between this 15 here and only 10 here along this coast. And this is a salinity, higher salinity, because in summer we have low salinity at the surface, and upwelling mix the subsurface high salinity water and brings a higher salinity to the surface. And of course, this is a higher water, which not stable, and soon will be a relaxation. As soon as wind will be slowed down, there should be a relaxation of upwelling. And we have high oxygen here because it brings from the subsurface area. And we examined what is the best season for upwelling, and we just examined seasonal monthly mean wind indexes. And we see this is a, for example, for Peters Great Bay, where is Vladivostok located, this is a most favorable indexes for upwelling is in winter and in fall and winter. But for this area, most favorable is a fall period, like October and early November. So this is a little bit different regime for the upwellings. And now I talk about the mesoscale structure. So this is a regional upwelling, but it consists of some mesoscale features. If you look to this satellite image, and blue is a cold water and yellow is warm water, and we put 3 mooring in distance about this, probably 100 kilometers at the coast. And this is a graph of the changes from the August till October. You see like simultaneous changes of temperature. This is a drop because of upwelling, because of western wind blown up, and then we have just simultaneous phenomena. So we called it regional upwelling, so Primorye upwelling system. But from other side, this image for the maybe in summer, we have a chain of such eddies which remind of waves, as maybe wave-like system of the eddies. And these eddies also generate the offshore, onshore water flows, which provide upwelling here and downwelling here. So, and generate local inhomogeneous in their structure, and also cause this This is a chlorophyll, and you see the filaments of the high chlorophyll water, or maybe some suspended matter water transported off the coast to the sea. So this kind of eddies generate exchange between the shelf and deep water here. And these eddies can be explained by propagation of the Rossby waves, topographic Rossby waves along the slope. And they are reproduced in numerical models, so it's quite well-known phenomenon in our area. And this is a structure of the eddy in this section, and the temperature, salinity, oxygen. And you see how this eddy upwelled water on the shelf. So my message is this: we have local upwellings all year round, but the intensity is different. But seasonal fall upwelling, when the whole mechanism works, eddies and wind induced segment pumpkin, this we have in fall season. And here's the changes of oceanographic structure. For example, there is images, satellite infrared images, it's only 11 days difference. Look at this area, there was warm water, and in 10 days we have this very cold upwelled water and formation of the eddies of mesoscale size. But the specific of our area, this upwelling happen in fall season. Our latitude is 43, which is a moderate latitude, and we have summer and winter with very big changes in temperature, and also heat flux from the ocean to atmosphere is very high in this period. And this is changes of temperature along this line from the coast to the open sea. And there is a days from October 12, October 27, and you see how the changes. This is a cooling because of release of heat to atmosphere, and this is very abrupt changes in the coastal area caused by this upwelling. So these our changes is combination of not only wind-induced or eddy-generated upwelling, but also atmospheric cooling. And the Sina thermocline, the faster cooling in this area. So means upwelling kind of the supporting mechanism for faster cooling. It brings cold water closer to the surface, and then it's easier to make this water cool because of heat flux. And there is a maybe a little bit complicated slide, but the message here, this, okay, I will probably skip this slide. And this is changes of primary production. This before upwelling and this after upwelling. Of course, this, as in other areas, there's a chlorophyll CVs images, satellite images shows, of course, and the other areas is changes in primary production, upwelling, increase primary production. But the changes of upwelling are different. Wide shelf and narrow shelf is this schematic shows it from our observations. The change is not very big on the narrow shelf, but on wide shelf we have very big changes because of intrusion of cold upwelled water. And in there all summer we have local upwellings here. So for example, if you look to changes in temperature at 50-meter depths, in the S1 is a wide shelf and S3 narrow shelf. This is different. This is like negligible changes here, and very big, about 10 degrees changes because of intrusion of cold upwelling water onto the shelf. And this is very important for us because one of the result of upwelling, which is important for our area, is ventilation of Peters Great Bay. So Peters Great Bay in this area on these schematics. And what do we have? This, for example, the observation of changes of temperature and surface and subsurface. In end of September, we have, by our mooring stations, we don't have big changes at the surface, but it starts cooling. But we have very strong, very big changes in bottom area. This is because of intrusion of upwelling water in the subsurface area. And this is very important because we have a problem with hypoxia. So this is a our bay is quite isolated. We have a river, we have a big city, and we have lots of nutrients, eutrophication in summer. And there is an increase, for example, decrease of dissolved oxygen in the bottom layer. We have hypoxia formation from spring, from March, April till August. And then we have abrupt changes because of upwelling water, which came from the ocean that's ventilate the inner bay, the shelf area. And for example, here there's another picture in the strait, Bosphor-Vostochny Strait, which connect this isolated bay with the open sea. And there is a changes of temperature during this spring, summer, and in late August we have very abrupt, maybe 10 degrees changes, and cold water came. And this cold water bring high oxygen to this area. For example, this is another example of, this is a section, not straight line, but a kind of complicated line, but this is one bay, Amursky Bay, here is Ussuriysky Bay, and you have cold water here in this area approaching, and we have low salinity because of river here, and we have, you see, very low oxygen on the bottom of this bay. This is a hypoxic condition, but this was beginning of October. And at the end of October, we have intrusion of upfilled water. And of course, its temperature dropped down, salinity increased, and it removed the hypoxic condition here. So upwelling is very important for our region. And this is another example of how big changes during this intrusion. This may be 10 degrees in 6 hours. So incredible big changes, of course, in influence to this ecosystem of the area. And what I say, this is another example of course, the interannual variability here. And what, and then finishing my talk, I like to say, upwelling is an element of seasonal changes here. And as I mentioned, there is upwelling area, and we have eddies, and we have reverse current from the North Korea during this upwelling regime. So schematically, what we have in summer, we have this primordial current, and we have this shelf slope eddies. But in September, October, when reverse wind, transition period between the monsoon, we have favorable upwelling wind. This formation of upwelling is this breakdown in primordial current, and this generate reversal current from North Korea. Then in November, this upwelling area increases, and we have formation of another current from Japan, from the branch of Tsushima current, with which warm water. And in December, we have this restoration of primordial current and this combination of two currents, which makes this system quite complicated. And this summer, we continued the research of this area, and we put two mooring systems in this upwelling. But we recovered it just recently, only at the end of December. And this is a preliminary results of the few peaks of the changes during these about 3 months. So then I hope to talk about these results later, and maybe next session. So the concluding, I like to say, this upwelling develops in the northwestern Japan Sea along Primordial coast during transition of monsoon. But an eddy dynamics lead to intensification of cross-shelf transport. We have local upwellings probably all year round, but this is a seasonal upwelling is most important. And water mass properties and primary production are the most prominent because of advection of filled water onto the shelf. And ventilation of hypoxic condition in Pieterse Bay by upwelling is very important. And also upwelling, I didn't talk about this, but upwelling brings high salinity water onto the shelf, which control winter convection processes and slope cascading for the next winter. I didn't touch this subject, but it's also very important. The winter ventilation depends on how high salinity of water preconditioned during the fall season. So that's all from me. Thank you very much.
Thank you very much, Dr. Lobanov. So, as usual, if you have any question, just put it in the chat and Dr. Lobanov will answer it. So we will proceed with the next presenter, Dr. Aleta Niguez, with the title Overview of Upwelling in Philippines. Yes, you may start, Doctor.
Okay. Hi. Good afternoon, everyone. Thank you very much for the opportunity to. Sorry. Wait, am I sharing my screen already? Let me see. It's okay. Okay. So.
Doctor, can you speak louder?
Oh, sorry. Can you hear me? Okay. Is this okay?
Yes, it's okay right now.
Okay. Thank you. So thank you again for this opportunity, and I'll be discussing some of our works on exploring the monsoon-driven upwelling and productivity, in particular in the southern Philippines. And I just like to say that actually there's still a lot to understand about our upwelling systems, and we've really only begun in exploring them. So. In terms of the general potential areas of upwelling in the country, these are potentially formed by the northeasterly winds during the December, January, February months, or the northeast monsoon. And this shows calculation of wind stress curl by our physical oceanographers. And this shows the during the northeast monsoon, the sites of positive wind stress curl in red, and the equivalent Ekman pumping calculations. So also denoting potential upwelling areas in the red zones. So these upwelling areas around the Philippines that are contributed to by this wind stress curl, and some of them more on the classical coastal upwelling dynamics. And we also see the higher chlorophyll A concentrations that are observed during the northeast monsoon. So if you look during the December month, the higher chlorophyll signal, and also this increases in January to February, and then decreases starting the transition winds of March, and then on to the southwest monsoon, where there's less chlorophyll concentrations around the area. But what I'll focus on for this talk is the work that we've done in the northern Zamboanga Peninsula. This is in the, I think Dr. Kemp mentioned this, the Sulu Sea upwelling. So this area here, that's quite distinct, and it's, I think, one of the more larger areas for upwelling in the country. And it's also considered one of the major fishing grounds in the Philippines. And what is typically caught there is very predominant are the sardines, so Sardinella lemuro in this eastern Sulu Sea area. So some of the mechanisms that contribute to this area's upwelling. So you have the coastal offshore Ekman transport, which occurs during the northeast monsoon. So in February, you have the northeast winds, and this is your sea surface temperature during the same period, showing the much cooler winds, which can extend to about 30 kilometers away from the coast. And it's a difference of about 4 to 5 degrees Celsius compared to during the southwest monsoon, where there's your southwest wind, and there's no signal at all of cooler waters coming up in the area. Another contributing mechanism is the wind stress curl, where there's a positive wind stress curl that has been calculated as well within this upwelling, identified upwelling region. So for this, the seasonal signal in this area for sea surface temperature in chlorophyll concentrations. Here in the left is a sea surface temperature, and during the November, which is transitioning to the northeast monsoon period, we start to see signals of cooler waters and also starting some a bit of an increase on the chlorophyll A, particularly for December and then to January and February, which tends to be more the peak of the period. And then March is still cooler, can have cooler water still, and also higher chlorophyll, and declining through April, and then eventually, again, the signal is warming water and less chlorophyll through the southwest monsoon period. So I'll also be presenting some of our work on a more finer scale studies that we've done in the site. We did field sampling for a few years, but I'll focus on February 2013 sampling, where we looked into adjacent sites in the Upwelling area. Here in we have Dipolog in the Sindangan regions. And it's interesting to see the differences within even just several kilometers away of Upwelling, where you have tended to have higher signal in this Dipolog Bay area and before transitioning to the adjacent region for temperature as well as the chlorophyll signal. These are the, we can also see this spatial variability when we look at the vertical profiles. So here again, it's the Dipolog, and there's two transects. So transect 1 is the one that shows the most, the strongest signal for upwelling, where you have that thermocline, the cooler waters coming up to the surface for the temperature, and also you have a buildup of chlorophyll in the more on the near shore side of the upwelling signal. And also the although for the Sindangan Bay, the upwelling signal is weaker in terms of the thermocline and just overall the chlorophyll concentration as well. We also looked at the actual phytoplankton in the area. So here again, Dipolog Bay exhibited the higher density in terms of the abundance of the phytoplankton compared to the Sindangan Bay, which tended to have the weaker upwelling signal. We actually also compared to another area which had a similar sardine fishery, but was watershed driven rather than upwelling driven. And interestingly, there were quite distinct phytoplankton assemblages in those 3 different areas. So there's more diatoms and in the Dipolog, which had a stronger upwelling signal and was also less diverse in terms of the phytoplankton species or composition. And there was increased representation of their dinoflagellates and higher diversity for the composition in the adjacent Sindangan Bay. So we also looked into how the fisheries related potentially to this upwelling region, and they're together with our colleagues in the area, they were monitoring as well the sardine catches in the this is Sindangan Bay, and then Butuan Bay is the one that was watershed driven, so we were also comparing that. But essentially, chlorophyll concentrations during tracked the sardine catches, the landed catch of the sardines, which were typically around the area quite well. And of course, the peak was during that time period of the upwelling, and the peak concentrations and also the catches of their sardines were significantly higher in this upwelling region compared to the watershed driven area. So in terms of the interannual variability, we looked into how this related to ENSO dynamics, knowing that, of course, in other upwelling areas, typically, or at least the big coastal, classical coastal upwelling areas, you have the El Nino promoting decreased upwelling. So here, we conducted the EOF analysis for sea surface temperature and chlorophyll. And the first mode explained most of the variability in terms of the cross-shelf gradient. So here I'm just showing the sea surface temperature results, but actually chlorophyll was much distinct or higher in terms of explanation power compared to sea surface temperature. So sea surface temperature, spatially the separated out into that upwelling region in red compared to the other surrounding waters, and this is the mode 1. And this is that cross-shelf gradient, and the temporal significant signals for that mode 1. Sorry. Oops. Yeah. For sea surface temperature here is shown in these plots, and then El Nino at this is the multivariate ENSO index at the bottom. And essentially there was a significantly correlated with the MEI, where it was the lower SST or upwelling occurrence during El Nino events versus La Nina dampened that or had a warmer water temperatures and also lower chlorophyll during La Nina periods. So this just looks into specific El Nino and La Nina events in the area. So within the El Nino events, there's still relatively high productivity within the so these zone 1 and 2 were the upwelling areas. So especially 2007 was quite a highly productive time. And while in the 2008 La Nina, there was a significant decline in the chlorophyll concentrations in that region. And we looked into the catches of sardine for this area and during that similar time period. Unfortunately, we have quite difficulty in long-term data, but our data came from just some general official reports in the country. So this is the Northeast monsoon season fish catch for the area, and it might be that it seems that during El Nino periods, there could be about higher or about the same as normal periods for sardine catches, while during La Nina, it's could be quite lower in terms of the catch, and that lower productivity and such a weaker upwelling could be the reason for that. And the potential mechanism for why this is the role of precipitation, rainfall during La Nina in our case, which sets up a barrier layer that weakens upwelling. So the rainfall anomalies were significantly correlated with the MEI, where you have higher rainfall and your La Nina periods in the area, and barrier layers where there's a strong halocline has been observed in the area during La Nina, although we haven't been able to go out in the field to actually sample this. We looked, of course, into the wind as well, if there was weaker winds, but the anomalies for using quick scat had no clear relationship with the ENSO events. So the hypothesis is primarily that the barrier freshwater lens could be preventing your upwelling. So, summary conclusion, essentially, upwelling and ensuring productivity in parts of the Philippines be highly driven by the northeast winds through wind stress curl and classical coastal upwelling dynamics. And then we're only beginning to understand the North Zamboanga Peninsula upwelling dynamics, both in temporal and spatial variability, where it appears that we have, of course, a seasonal signal, and you have interannual variability that can be affected by ENSO. And there's interesting spatial variabilities in physical and biological characteristics within this upwelling area. And these can have significant implications on the sardine fisheries. So we really need to understand this more in order to provide more science-based information for the fisheries management in these areas. With that, thank you very much. These projects were funded by our own science and technology funding agencies, and of course my co-researchers for the various studies included in the talk.
So thank you very much, Dr. Alita. Okay, I think we move to the last presenter for today, Dr. Wichia, with his presentation title of Chlorophyll Variability in the Tropical South China Sea.
Thank you, Dr. Zuraini. Can everyone hear me?
Pardon?
Can you hear me?
Yes.
Okay, so thank you, Dr. Zuraini, for introductions, and thank you, first of all, thank you, Dr. Fatir, for the invitation. So here, I would like to share some of the work that me and my colleague, and especially my master student, Muhammad Isma, has been doing for the chlorophyll variability in the South and South China Sea. So thank you to the co-researcher, Dr. Cheng, Dr. Chow, and Prof. Azizan. So just going to turn the pointer. Right, okay. So first of all, a quick shout out to the funding agency, the Ministry of Higher Education Malaysia for the FRGS grant, and then the High COE grant, as well as the FIO Joint Center. And most importantly is the NASA, the European Space Agency, the Copernicus, NOAA, and ECMWF for making the data available, which this talk is going to have a lot of satellite and reanalysis data. Okay, first of all, I would like to draw your attention to this animation. So on the right panel, that's the monthly chlorophyll A. So I put it on from 1997 onwards. This is a merged globe color product from CSA.
Sorry to interrupt, Dr. Wichia. Could you please make your presentation into slideshow?
Is it not in slideshow?
Yes. Full screen. Is it? Is still in Microsoft PowerPoint form? Yes. Currently. Oh. Okay. Now.
How about now?
No. Can you do it again? It's still we are still seeing your screen, not the full slideshow. I think we're still seeing your screen, but I think this will work as long as I think it's we can see it clearly. So anyway, it should be all right. Because when you share the full screen, it become only half screen. I'm not sure why, but
maybe I try.
It's okay. Maybe you can just you can continue.
How about now? Is it same?
It's still the same, but I think you can continue because,
Okay, so sorry about the technicalities, difficulties here. So please bear with me. I hope you can see the animation is moving. just want to highlight the red box, the square box is where if you can see my pointer. So, and on the left panel is where the bathymetry. So I just want to quickly highlight what the focus for this sort on Southern South China Sea is.
Sorry, Wicha. We can't see the animation. It's just just the screen. Just now we can see it, but now I couldn't see it. I think you are using multiple display, isn't it?
Yeah. But
So
I make the mirror display.
Yeah, I think maybe that's the.
Okay.
So yeah, if you use two screens, you might need to, plug out one of it.
Do you mind if I switch off because I need to switch the screen then?
Yeah, you can share again. You can switch off this one.
Okay, actually my the other screen doesn't work. I'm sorry. Maybe I have to switch to another computer because the other screen I have problem with the other screen. I have to switch to another.
I'm seeing the animation is working now, but sometimes you might have problem throughout.
Okay, maybe I just present like this if you don't mind. I hope that everyone can see it clearly. If I enlarge a bit. Is it better?
Yeah, we can see the animation. Yeah, I can see now.
I think I'll just proceed with this without sharing the full screen. Yeah, I'm very sorry about that. Yeah, I don't know because of the mirror display. Okay, just back to this one is just to highlight the southern part of the South China Sea. You see the left panel is the bathymetry, which the blue contour line. This is the blue contour line. This is where the 100 meters depth. So if you compare the northern part, you will get like basically about 70% is the deep basin, which you have more than 100 meters, and then some is close to more than 1,000. But if you focus on the south, you see there are a large portion of the Sunda cell, which is less than 100 meters. So this with regard to, where it's quite interesting, the talk from Dr. Kem and Professor Wong, and the topography upwelling. So on the animation, I just want to show the animation so that you can have a grasp of how dynamic is the chlorophyll concentration within the South China Sea, especially in the southern part. You see the Dr. Cox presented the upwelling in the east coast of Malay Peninsula, and then this is famous Vietnamese upwelling, and this is all in the southwest monsoon or the boreal summer. And I would like to highlight also that the Dr. Cox showed that there's upwelling in the Sabah or north of Borneo, Sabah tip, but actually in winter time you see the overall the north of Borneo actually the chlorophyll actually increase. So this region is very dynamic in terms of the chlorophyll concentration. Move next. So this slide shows surface temperatures. This is the average value for the boreal winter on the left panel, and then boreal summer on the right panel. So I put the same color bar, so you can see very clearly in the winter time or the northeast monsoon driven, you get really cold sort of floods of cold water into the southern part of South China Sea. And the blue contour lines indicate 28 degrees Celsius. And if you look at the summertime, then the 28 is basically very close to only this bit. The rest is pretty much more than that. But I would like to highlight, you still can see the sort of the upwelling that Dr. Cox presented. over from along the east coast of the Malay Peninsula. Okay. For the chlorophyll concentration, so this 22 years, so sort of average, you see the north during the northeast monsoon, it's pretty much high all over except for the sort of the deep basin. So the red contour line is where the sort of 0.15 milligrams per cubic meters. So this is sort of for phytoplankton biologists indications of high, or can be at some point indicator of bloom. So you see most of the southern part is pretty much higher than 0.15 milligrams per cubic meter. And in contrast, the sort of during the southwest monsoon, the high chlorophyll water sort of only subject to very coastal or shallow areas within the whole southern South China Sea. So in terms of the long-term variability, or not long-term, probably this is about 22 years time series. The blue line indicates the SST, where the red line indicates the chlorophyll A concentration. So you see this is, so the top panel is the monthly mean. So it's always you have the low SST during the close to the winter time or the year end. Then in contrast, where you have the high value of chlorophyll concentration. So that's like the opposite, which is, yeah, many experts already presented earlier. So I want to highlight that's another sort of a smaller peak during where the summertime chlorophyll concentration increase. So this is the, and then in terms of the anomaly, you can see the SST anomaly can go up to more than 1.5 during this 98 El Nino year, small in 2018, and we get a more and more sort of higher anomaly in recent years. So it's from this 2013 onward, and then it actually affects sort of the chlorophyll concentration. If you look at the anomaly, especially in 2016, where you get in winter time, you don't really have a sort of a peak in winter peak as like a usual year. So it's hard to tell if from just the time series. So look at the empirical orthogonal functions analysis. This is for the chlorophyll A. So the first one, the PC1, explained 41% or 42% of the baby. And you can see it's pretty much the whole southern South China Sea is sort of a increase, or it's a positive value. And looking at the temporal variability, then you see that the peak is pretty much the one that I presented just now. So it's winter time, peak, and then summertime, you get the reverse, or sort of not summertime, but in pretty much May, April, May, June. So the bottom right, that's where the monthly pattern. So you see the April, May, June, we get the lowest, and then slightly increase during the June, July, August, September, and then the highest is where the sort of during the winter, for the winter. And looking at the sort of the physical driver, so this is a regression of, sorry, this is the percentage of chlorophyll difference. So this one clearly shows that the increase is mostly dominated during the winter time peak of the PC1. So the dot represents the significant level. So most of these, you see that quite significant. So I would like to highlight that the coastal region, maybe that's what the camp is explaining, that it could be some of the I don't know whether it's downwelling features, but for the north of Borneo, this is a typical upwelling or sort of wind driven, because it's parallel to the coast, where the coast is on the left side. So then we go for the one that I presented earlier, the monthly low in terms of the PC1. So the April, May, June, this is where you get the change, sort of the low of COR3A for the PC1. And looking at the regression, so this is the regression with SST. So clearly that SST, when you have the high and then where SST is low, so this is nothing surprising. And the composite of the December, January, February show that this is where the low COR3 as well. Then we want to highlight the so this is the low of the high SST during the April, May, June. So this one indicates this opposite, and it's all like a significant value. So this is composite of April, May, June. And regarding the wind, so this is the wind regression with the wind stress. So you see that for regress, when you regress with the first UF for A, then it show clearly, that's all the wind sort of brought in the cold water, and this is probably the induce of mixing, and then the high chlorophyll water in general during the winter time. And then this is what I would like to highlight also, the cam sort of show just now. It could be the wind and can have some impact on the coastal downlink perhaps, and then maybe have some of the anomaly high in this part of the area. Okay, and then for EF2 or PC2, so this will contribute about 20% of the variance. And you see, this one is clearly shows the high is in this bit of the water from the east coast of Malay Peninsula up to the famous Vietnamese coastal upwelling. So as you can see from the temporal, as expected, the high is actually in during the summer, boreal summertime. This is a reverse from the first PC, and the low is usually during the winter time, as you can see from the temporal coefficient plot on the top right panel. And the bottom one, this is also highlighting the monthly variable for the PC2. So you see the low is during pretty much minimum in March, and the high is within during July and August. So what about the changes of COR3 for PC2? So you see the changes the same as the one that we showed just now. It's clearly that this bit is dominating the PC2. So the changes in terms of the increase of this COR3 waters from east coast of Peninsula up to the sort of the coastal Vietnamese upwelling, and this is in the July, August, September month. And then this, in contrast, the low is in February, March, and April. But here you can see sort of the low is over here, the one that is really, but on the other hand, you get sort of the high north of Zamboanga. So you can see some of the features here. Okay. So I just want to, this one is a regression. So this is a bit interesting. So we are still figuring why is that, because we don't really expect to see the regression of the low temperatures here. So this is still work in progress. So yeah, it's more thought needs to be going analysis for this bit. So let's go to okay, this one is okay, this is for the February. So this one is because of the basically winter time, we get the low. And I just want to go to, okay. Okay, for the wind type, okay, so and again, we see that the PC2 is dominated by this coastal upwelling from east coast of Peninsula up to. So this is from the wind stress. Then you can see clearly that wind driven. It's all driven by the wind. Okay, it's explained before by other people. So just want to, for the interest of the regions of interest, and I just want to show that how the chlorophyll variability change over within some of the regions. The top one is where the plot that I showed earlier. This is for the whole southern South China Sea basin. So you get this peak of SST in summer and cold in winter, and in response, then you get the cold, so high chlorophyll water in boreal winter, and then the sort of low in boreal summer. But then we get the sort of smaller peak during the boreal summertime, June, July, August. And for the East Coast, I did a sort of focusing on just the region over the East Coast of Peninsula. The pattern is pretty similar to the sort of the whole southern South China Sea basin, where you get high winter, high chlorophyll winter, low. General is high in winter, but then you get a smaller peak in summertime where you indicate the upwelling of the cold water, and then high concentration of chlorophyll. But then when you look at this region of north of Borneo, you don't really see that sort of summer peak, small summer peak. It's pretty much low during summertime, and then the peak is only clearly shown during the December, January, February, March. So the take-home message is, or the summary is, the chlorophyll variability in southern South China has a very strong seasonality, mainly driven by the monsoon. So we have they respond really strongly with the northeast and southwest monsoon, but the response vary geographically. So it could be the topography, the one contributing to the variability, and the first and second UF can explain over to 60%. I didn't show the other UF. We get sort of EF 3 and 4 is the inter-monsoon season, and then we have like about 10 UF can explain up to 80% of the variability of chlorophyll A in this region. And PC1 saw more of a general pattern, which is the basin-wide increase of chlorophyll A from December to February, indicating a strong influence of northeast monsoon. While PC2 clearly show the southwestern monsoon dominate, and then the influence on the coastal upwelling from Malay Peninsula to the Vietnam coast. And then the statistical regression analysis show that wind stress curves SST has a strong influence on the PC for chlorophyll A. Yeah, that's all my talk. Thank you. I'm sorry for the technical issue.
Okay, thank you so much, Dr. Wisya. Okay, I think that's all for today. I would like to thank all the speakers for their knowledge sharing, and I hope all of us benefits from this workshop. So I will pass back this session to Dr. Fazil for the summary.
Thank you very much, everybody. I would like really to thank all our speaker from Wangzi this morning, and then we have Dr. Cam from Australia, Prof. Isa Iskandar from Indonesia, Dr. Ernest Kok from Malaysia, also Prof. Wang from China, and Dr. Lobanov from Russia, Dr. Iniguez from Philippines, and also Dr. Wisya from Malaysia. So thank you very much for all of your contribution. I think it's a very unique and a comprehensive presentation. It covers from basic dynamics up to different characteristics from ENSO, and we look at different bathymetric profiles and how it impacts outwelling. So all of this combination really portray the what we are doing in the group. So we are not basically looking into only the physical or the dynamics aspect, but we also want to look at the other aspect of upwelling as well. So we can really provide a good information for our researcher, especially focusing on this area. So for tomorrow, I really hope that all scientists can join us again around 10 o'clock Malaysia time. So we have so our program will be, I will give you some overview on what's we're doing in the groups, our previous plan and how we execute those plans, and how we're going to plan for the next chapter of this group implementations. So, and we hope for, I mean, those forum we will open up for discussion with all other scientists. We welcome ideas from our fellow researchers, and we hope that we can come up with a resolution for the groups tomorrow, and hopefully those resolutions can guide us for a much clearer direction for the groups, and also that hopefully we can contribute to the UN Ocean Decades and also the IOC-WESTPAC. So that's all from me today, and I would like to thank all the secretariat for the organization, especially from our secretariat in Bangkok, Wenzi and Nachapa. So again, thank you very much, everybody. I hope to see you tomorrow around the same time. Thank you. Bye. Esok nak gambar. Boleh. Sebab ini ramai sangat. Esok kena on ni, tak boleh.